Hello, this is Mr. White, and this video is on the quotient rule and the tangent line equation. Now, there really is nothing brand new in this video that we haven't done before, but it is just at this point in the course, kind of a good review of some of the skills we've acquired up till now. And finding a tangent line equation is just something basic that you really just need to be completely confident in calculus. So we're going to be asked to find the tangent line equation for the given function at the indicated point. And then we're going to, of course, verify our answer with a calculator. So let's start with the non-calculator processes. And let's start to think, what would we do if we were tasked with finding out what this function looks like and then what its tangent line looks like if we weren't allowed a calculator at all? What could you figure out from this equation about the function graphically? And don't tell me nothing, because that's not true. What would that equation tell you about the graph? Well, we might start by looking at the denominator, and we could tell from that denominator that we're going to have a vertical asymptote at x equals -2, right? What else could we do? Well, we could plug in 0. 0 is always, typically is a very easy number to evaluate. So if I plug in 0, I can very clearly see that for an x value of 0, I'll get a y value of 1/2. And of course, there's nothing to stop me from just plugging in more and more points at will, but that's not really the most sophisticated way to go. So 0, we'll stop at 0. What else could we do? Well, think about how limits would help us. Yes, limits ultimately yielded derivatives, which is super cool, but what about other limits? Or other uses of limits and what they can tell us about this graph. What if we took the limit as x approached infinity? Well, we could do a limit analysis and find that the y value is also going to approach infinity. Remember that whole thing of saying what happens is x gets really, really big and we cross this out and cancel and all that stuff. So we would determine that, we could do all that and determine that the y value also is going to approach infinity. And that would tell us that the graph, as the graph goes to the right, that it also goes up. We could look at the limit as x approaches -infinity. And we could do a similar analysis and find out that the limit is -infinity as well. So as we go to the left, the graph will go downward infinitely, plunge downward infinitely. We could do the limit as we approach the asymptote. We could do one-sided limits. So what about as x approaches -2 from the negative side? We would find out that that also is -infinity. So that's what tells us that instead of the graph riding upward along the asymptote as it approaches from the left, that tells us that it goes downward. And if we were to approach the vertical asymptote, -2, from the right-hand side, we would find that that is positive infinity, and that's what tells us that the graph rides upward along the asymptote as we approach from the right. So we could tell there, let me redraw that one, like that, and we could tell that at some point it goes through this point, and there's a minimum, and whether that minimum occurs at the y-intercept or whether it occurs at some other point, we will need some of our upcoming calculus skills to do much further analysis on that. Some of what we'll do in the future is we'll study the derivative, and we'll find that whenever the derivative is positive, that means the graph is increasing. And I hope that's intuitive on some level for you. That we would find that whenever the derivative is positive, that's a part of the graph where we're increasing. We'd also have an increasing portion of the graph right here. We find that whenever the derivative is negative, that means we're at a decreasing section of the graph. And we would use that and then discover where our extrema are. Where a graph switches from increasing to decreasing is where we would have a local maximum. And when it goes from decreasing to increasing, we have a local minimum. So I'm kind of hinting at what you can do already right now and where we'll be going with all this calculus stuff. But let's get back to this problem at hand. We're being asked to find the equation of the tangent line when x equals 3. Now, our book sometimes will give you both coordinates. So again, I'm kind of hinting at that there's a, I could have given you both the x and the y coordinates, but I'm just going to give you the x coordinates, and we'll deal with that. What do we do first? Well, let's go ahead and find the derivative. So I'm going to move this graph off to the side here. All right, and let's do our quotient rule. I'm looking and seeing, is there any algebraic simplification I could do here that I should do before I do the quotient rule? I don't really see any, so let's jump into the quotient rule and say f prime of x equals the bottom. I'm going to go through this a little bit more quickly, pause as needed, times the derivative of the top, which is going to be 2x, minus the top, x squared plus 1, times the derivative of the bottom, which is just 1. All over the bottom squared. Let's simplify. I'll distribute that term on the top and get 2x squared plus 4x minus x squared minus 1, distributing that negative, right? All over x plus 2 squared. And then up top, I've got 2x squared minus x squared. That's going to give me x squared plus 4x minus 1. All over x plus 2 squared. And again, let's not bother foiling out the bottom. That is our f prime of x. Now, we, of course, want to know what the derivative is at an x value of 3, right? So let's go ahead and figure out what that is. Let's plug in 3. F prime of 3 is going to equal 3 squared plus 4 times 3 minus 1 all over 3 plus 2 squared. And of course, that's going to be, let's see, that's going to be 20 over 25, which is going to reduce to 4/5. Okay, so let's think of what we know now. We know the x value that we're interested in. We know the slope is going to be 4/5 at that x value. And if I look at my graph, that is consistent with the graph that I had here. If we look for an x value of 3, we could believe that the slope is going to be 4/5 at that point. And we're expecting a positive y value there as well, based on our previous quick analysis. So where are we going to get the y value from? Well, we're going to get that from the original equation. So let me copy this down here. And let's figure out what the y value is, aka the f of x value. So let's plug 3 into this function. And I'll plug it in here and here as well. And that's going to give me 9 plus 1 up top, or 10, over 5, which will give me 2. And guess what? We have all the pieces. Let's bust out that point slope form of a linear equation. That's the y minus y1 equals m times x minus x1. So again, this is some review. We've done this before, but it's good to go over it again. Reminder that the grown folk notation would look more like this. F prime of x1 times x minus x1. And then over here we'd have y minus just f of x1. And in this case, x1 equals 3, and we've already figured out what the y value and what the derivative is going to be for that value. So let's just plug everything in. We said for slope, we were going to get 4/5. That was our f prime of 3, right? So scroll down here, and that's going to be 4/5. The x value itself was 3. And then over here, we just determined that the y value is going to be 2. We said f of 3 was equal to 2. And as I've said many times before by now, you may put a box around it right now. The only reason to go any further is if you're going to check by calculator, which is never a bad idea. So let's go ahead and distribute 4/5 times x minus 12/5. Let me just temporarily write minus 12/5. And I'm going to go ahead and add that 2 over to the right side. So that's going to be plus 10/5. That's my how I'm writing 2, correct? So minus 12/5 plus 10/5. That simplifies to just minus 2/5. I'm going to go ahead and just erase it and put it there. So again, whether you write it in point-slope form or slope-intercept, either is technically correct, although I generally recommend you leave the point-slope as your final answer. But let's go ahead and check by calculator. Or actually, let me bring the remainder of the problem onto the screen. We were to use the graphing utility to graph the function and its tangent line at the point, and use the derivative feature to confirm the results. It's a little bit redundant there. But let's bring the calculator up here. So here is the function. Here are my window settings, if you are interested. And here's what the graph looks like. And notice that it is very consistent with what we proposed earlier. So let's go to second calc number 6. I'm pressing the number 6 on the keypad, and I'm typing in an x value of 3, and I'm confirming that the derivative, we said it was 4/5. The calculator says it's 0.799999. We can say that within our usual calculator goofiness that is the same thing. 4/5, 0.8, that's the same thing. And again, we said up here that we had a derivative of 4/5 when x was equal to 3. All right, so what we really just did there was use the derivative feature of the graphing utility. I'm going out of order here a little bit. As far as graphing the tangent line, I could go to y2, and I could just go to y2, and I could type the tangent line equation in there, but you know, let's go ahead and just use the tangent feature of the calculator. Remember that that's second draw, and we can go to option number 5, so I'll press 5 here. Oops, let me try that again. I got the graph displayed, second draw, 5, and then type in 3, enter, and I see my full tangent line equation. And again, is that the same as what we got? Well, we said that 0.799999 was essentially the same as 4/5 times x minus something that is essentially 0.4, and that's what 2/5 is, 0.4. So we've successfully graphed the tangent line and confirmed that the derivative is the same. Let's call this problem done.